Hi, so this is assignment number one, Jane's test to be organized or not, and it's by it's been done by group number six. My name is Andy.
I'm Tom.
My name is Teja.
So the problem presented in this assignment is about a professor named Jane of mathematics. She receives a pile of papers every day, and the number of papers varies. But let's assume that on average, p amount of papers land on her desk. She has to fetch a couple of papers every day for her research, so the number of papers varies. But let's just assume that on average, she picks S amount of papers per day.
In the question, it states Jane receives an average of P papers on her desk and she picks S papers per day. She also has some of the papers she considers to be her favorite. Since Jane may eventually want to return to these papers, she'll have to search for them in the pile. The searching through this stack cannot be accomplished without some sort of sorting algorithm. This means if she has to sort the papers, it's easier to use probabilistic analysis.
So now that we've decided that she should be sorting if in the case that she has a favorite paper within her list of papers, let's decide what type of searching we should do. So on the right, we have essentially a worst case scenario where we have an example stack of papers that she could have on Jane's desk with her favorite, the paper she would want to search for, being at the very end of the stack on the bottom. So in this worst case scenario, we have P equals 8 pages, her favorite stack on the bottom. If she wanted to find that favorite paper, she would have to go through all 8 pages, essentially making her runtime O of 8. This means that even though over the course of the year the stack will definitely grow and P will definitely increase, the runtime will remain linear. It'll still be O of P, with the worst case being a whole stack of papers, but the one she wants to find or the one she wants to search for being at the bottom of the stack. Go for it.
Hi everyone. Today we're going to talk about assignment 2, apartment hunting, which is created by group 6. My name is Teja.
My name's Tom.
My name is Andy.
Let's talk about the problem. A real estate agency in Manhattan has developed an app to offer its listing for lease. The app is similar to a game. The app is called Ranter. There are n units for lease. Let's call the user Tom. When Tom starts the app, Renter shows one property at random at a time. Tom either likes or dislikes the apartment. If Tom dislikes or likes a case, cannot change his decision. All swipes are final. Tom knows he can only like n cases. After that, Renter will stop showing the cases. The game will end when either Tom has picked all his n cases or the database ran out the cases. When Tom likes a unit, it does not mean he gets the apartment. It has to be approved by the owner of the unit. Help Tom to make the best decision while using all his N options. He has picked almost best cases.
So the assumption with this problem is that Tom picks the almost best cases. This is assumed that this is assumed to mean that in a situation where Tom has n amount of likes and n amount of properties, that he will always find either the best house of all the viewed properties or the best house out of all the n properties. If the last like is the last on the list. So we have two situations. For the first situation, Tom is giving a list of 10 houses and a maximum of 5 likes. He views all 10 of them, and on the 10th house, he uses his last like, as it meets his conditions and is better than all his previous likes. This would be the best case scenario because his last house, the last house he liked, is the best houses out of the 10. So for the second situation, Tom is also given 10 houses to view and 5 likes as the max. He views only 8 properties, and on the eighth house, he uses his last like because it meets his expectations and his conditions. And it's also better than all his previous likes. However, let's say that house number 9 was better than number 8. This would mean that although that although his house has met all his expectations, there were better choices. This would mean that it would be the almost best case. So the solution we've thought of for this problem was using the hiring problem method. And the hiring problem has two major components, the condition and the list of options. So for the condition, as not clearly stated in the question what determines if Tom likes or dislikes the house, we can assume that he has some requirements for the property. These requirements become the condition in which we either swipe right or swipe left on the next house. And as for the option, the n houses we look at will constitute the list of options we decide on. If the property being viewed meets a set of requirements or conditions, then we will swipe right. If not, we will swipe left.
So to demonstrate the runtime of the application, or just an idea of how it would work, we've modified the code from the hiring problem. So in the hiring problem, usually the condition would just be a changing variable dependent on whatever the most recent employee you hired was. In our case, we've decided to make that condition a constant, meaning it's not going to change depending on the houses we swipe on. We're going to go through each of our list of properties, and we're going to just mark it based on that condition. If it meets the condition, it gets a like. This means that we can easily run out of likes, but if there's a house at the end of the list that was, let's say our condition in this code was 7, and let's say we've used up all of our likes, and the last house we used up our likes on was an 8. It was a great house, but it was only an 8, beat our condition of 7. Let's say the next house was a 9. We've run out of likes, but there was a better case scenario. That's why all of these are almost best cases. In our code, we're going to swipe right, we're going to lose a like, and we're going to lose a house, versus if we don't swipe right, we would just lose a house, and our code's going to run either until we run out of likes or we run out of houses. Next slide. Essentially, this makes the runtime completely dependent on whether he runs out of likes first or whether he runs out of properties. In the hiring problem, the worst case would translate to hiring all of your employees, but in this case, it's going to be the worst cases if you have to go through all of your properties or go through all of your likes, which is essentially mandatory. This makes the runtime linear, and it's going to make it either O of little n if he runs out of likes first, or O of big N if he runs out of properties first.